Hello again, everybody. I hope everybody is doing well and is being able to cope with this crisis as well as they can. I hope you're trying to keep up with this material as I'm trying to do as good as I can to present it to you. And if you have any questions, I always recommend just send me an email and I'll respond relatively quickly. So I hope all of you are well. Let's continue with this chapter now on light and matter. And I wanted to remind you that we started talking about what are the most important things that we've learned so far, at least in this chapter. And one of the things is the concept of electromagnetic radiation is a wave, okay, and it travels at the speed of light in a vacuum, and it slows down when it goes through any other material. And when it slows down, it bends, it refracts. And I remember I showed you the slide that had the little diagram of the pencil looking like it was bent when it was in the water because the light rays bend when they go through the water and not through air as much. Also, I wanted to remind you that electromagnetic radiation is produced anytime a charge in an atom is in motion. And for all practical purposes, everything in the universe, everything, has charges in motion. And when these charges, like electrons and protons inside the atom, when they move, they create electromagnetic waves. As I told you, moving electric charge creates a magnetic charge, and a moving magnetic charge creates an electric charge. So they're tied together. Electric and magnetic fields are tied together, and it's given off by everything in the universe. And we said that we can break them up into these 6 categories that I showed you here. Here are the 6 categories of electromagnetic radiation, from the wavelengths that are the longest, the radio, to the wavelengths that are the shortest, and also the shortest and most energetic. So these are the 6 categories of waves: the radio, infrared, visible, ultraviolet, X-ray, and gamma ray. Those are every possible wave has to fall somewhere, electromagnetic wave will have to fall into this category. And as I told you before, you remember that white light, visible light that we see, is actually made up of different colors, different wavelengths of light. Okay, from red, which is the shortest wavelength, to blue, which you can see here, which is the longest wavelength. Let me let you look at this slide here. And what it shows is it shows the electromagnetic spectrum really in terms of how many waves, how big each one of these categories is. On the previous slide, each of those categories was a fixed length. However, in reality, that's not true. Okay, if you can see here, the radio region of the spectrum, here's radio, here's infrared, here's visible. Look at that little part visible. Here's the ultraviolet, here's the X-ray, there's the gamma ray. Okay, the radio region of the spectrum is one of the largest region of the spectrum. It goes from very long wavelengths to shorter wavelengths. Okay, we start off, radio has longer wavelengths, and you can see here is the advance of the spectrum. You can see long wavelengths to really, really short wavelengths as we go over to the gamma rays. The radio waves, okay, have wavelengths on the order of these little pictures that I show you right here. All these pictures represent the size of the wavelength for each one of these categories. So you can see under the category of radio, up to about this region, the radio waves have wavelengths on the order of the sizes of things that you see here pictured. The wavelengths can be as big as sizes of mountains, maybe many kilometers. Could be the size of a skyscraper. The wavelength could be the size of a skyscraper. The wavelength could also be the size of a human or up to a fingernail. So that carries a broad region of the electromagnetic spectrum is in these radio waves. And then as I get into the next category, as the wavelengths get shorter and shorter and shorter, we come into the infrared region of the spectrum. The infrared region of the spectrum has wavelengths that are on the order of a pinhead and a little piece of dust. That's about the size of those wavelengths. And remember, infrared wavelengths are heat energy. Heat is an electromagnetic wave. All right? Finally, we come to the visible. And this is the region that we are able to see. Okay, this is the only region for the wavelengths, the electromagnetic waves are sensitive. Our eyes are sensitive to the electromagnetic waves in the visible part of the spectrum. And if you look here, if you go straight down, you'll see that the wavelengths are on the size of a bacteria or a virus. They are tiny. The wavelengths now are very, very small. And they go from the red on the left-hand side of the visible here is the red, and on the other side, and being a very small thing, are the blue. So all the wavelengths, these are the only region of the spectrum. This one right here is the only region of the spectrum that's visible to your eyes. You can't see all the other ones. Right after now, the visible comes ultraviolet. And in ultraviolet, you can see right here, we're talking about wavelengths that are on the size of a virus. As we move up into the X-rays, we go into wavelengths that are the size of an atom. And gamma rays have wavelengths even tinier than the size of atomic nucleus. So you can see we've gone through a broad range of sizes of waves. We go all the way from the size of a mountain, wavelengths that are about the size of mountains, to wavelengths that are the size of the nucleus of an atom. And as we move to the right, as we go further and further to the right in this direction, we're going to more energetic waves, higher energy. They can do more damage. And as I told you, the gamma rays of all the rays have the ones that have the most damage, can do the most damage. Let me show you here. Here is an image down here below in the lower left-hand corner. It's an infrared image. This is an image of the heat radiation, the infrared radiation coming from a detector that is sensitive to infrared waves. And what it does, this detector will convert the infrared waves into visible wavelengths that we can see them. And as you can see here, there's a color chart for temperature. The coolest things in the picture will be purple, and the warmest things will be yellow to white. Those would be the warmest things. So you can see from this below that we're looking at the image of two people sitting down or standing up somewhere. And then as you can see, the wall behind them is cool, relatively cool. It's the coolest thing in the photograph, this infrared image, a thermal image. And you can see here, look at the forehead of the woman here, and look at the forehead. I assume it's a woman. And look at the forehead of this person right here. You can see it's glowing yellow. It's the hottest. That's because that is the warmest area of your body. That's why when you were a little kid, your parents put their hand on your forehead, because that was sensitive, most sensitive to the temperature of your body. All right. You can also see that right here in the neck area, that's also an area that all the blood vessels are flowing, and that's where we're picking up the temperature. You also look at the nose, the tip of the nose. Notice how cool the tip of the nose is. That's why when you go out in the wintertime, your nose gets cold. There's not a lot of blood flowing there, so that's going to get cold the fastest. But what I wanted you to show is this is a way of converting infrared energy to a way we can see it, and you need some sort of a detector to do it. And this thermal detector converts infrared energy into visible so that we can see it, and then color codes it that way. There's a lot of material on this chart. I also want to explain to you this below right here. What this is a chart showing which wavelengths of the electromagnetic spectrum can pass through the Earth's atmosphere. The Earth's atmosphere is not transparent to all the wavelengths. That is, all the wavelengths don't necessarily pass through the Earth's atmosphere. Okay, and if we remember, here's the radio, here's the infrared, the visible, the ultraviolet, the X-rays, and gamma rays. As you can see from this chart below, what's in the darker blue shade is the area in which the atmosphere is opaque. Opaque meaning it cannot transmit any of that radiation through it. So most of these radio waves, a lot of these radio waves are blocked by our atmosphere. However, you can see here we have what we call a radio window. There are certain wavelengths of radio waves, and about half of them can make it through our atmosphere. So as we said, only some of the radio waves get through our atmosphere. Okay, so our atmosphere can be transparent to radio waves right in this area. You'll also notice that as the window now closes up here, it's darker, meaning it's closed. That doesn't let this electromagnetic radiation come from space through our atmosphere. In the infrared region of the spectrum, the infrared region of the spectrum is opaque. The atmosphere is opaque. We can't feel those infrared waves coming in to the Earth's atmosphere. They are blocked. So infrared is blocked. And then we get another window. We call it the optical window. That's the window in which the visible light comes in. Because we can see visible light from outside in space can get through our atmosphere to our eyes and to our telescopes and to our instruments. That's how we can see galaxies. That's how we can see the moon, the sun, because the visible light from those objects can make it through our atmosphere. And then you can see as we go further and further down in the ultraviolet, there is a slight little window in ultraviolet that's transparent. Some of the longer wavelength, this is the left-hand side meaning longer wavelength, the near ultraviolet, some of those can actually get through the atmosphere. And that is what gives you a suntan. When you go out in the beach in the summertime, the sun puts out radiation in all different wavelengths. Some of those wavelengths fall in the ultraviolet and they can pass through our atmosphere and tan and burn our skin. The more dangerous ultraviolet waves, the far ultraviolet, cannot penetrate, thank God, because as I told you, as we're moving to the right here, they can do more damage. And of course you can see X-rays and gamma rays primarily are blocked by our atmosphere. So you can see the Earth is an ideal place to really live because most of the dangerous waves can't penetrate the atmosphere. The only ones that penetrate, and that's what's shown in this here with all these windows, is we can see some infrared, but let's not even consider that. Let's assume all infrared is blocked, but visible light can come through and some ultraviolet and radio. So radio, visible. Those are what I want you to remember are the two windows in the Earth's atmosphere. We can receive electromagnetic radiation from space only in the radio and only in the visible. All the other ones are blocked. So if we wanted to get some information from objects that are in space at other wavelengths, in the ultraviolet or in the X-rays or gamma rays, we would have to send a probe up high above the Earth's atmosphere before that radiation is blocked. And you can see here, this next slide, it just summarizes that, is that the Earth's atmosphere, I'd like you to remember, is transparent in two areas. In the radio, and that's above the AM radio band, that's what AM radio, above, so but for all practical purposes, it's in the radio band and in the visible. Those are the only two wavelength bands that make it through our atmosphere, because our atmosphere absorbs all the other wavelengths and blocks them. So if we want to do astronomy at other wavelengths to determine what kind of radiation a lot of these objects are putting out, on the Earth's surface, we're limited only to radio invisible. However, if we put a space probe above the atmosphere, okay, we can do infrared astronomy, ultraviolet astronomy, or X-ray astronomy. We cannot do those from the surface of the Earth. We can't do them from ground-based telescopes. We have to put telescopes up in space. And if you remember, we talked about a new telescope that was going up in space called the James Webb Telescope that's going to hopefully go up in the next year or so. That telescope is an infrared telescope. And so it has to go above the Earth's atmosphere in order to gain information about what's happening in the universe. Let's look at now, I want to talk to you a little more, have you understand about temperature, okay? And specifically, you probably know about two different types of temperature scales. The temperature, the way we measure temperature here in the United States and in North America, okay, is through something called the Fahrenheit temperature scale. In the Fahrenheit temperature scale, water freezes. Does anybody know where water freezes? Well, at what temperature? Water freezes at 32 degrees, okay? And water boils. I bet people don't know where water boils. Water boils at 212 degrees. That's the Fahrenheit scale. But most of the world, besides the United States, some areas in North America, only really the United States, but every other country looks at the Celsius scale or the centigrade. We call it centigrade or Celsius scale. And that scale is a lot easier, I have to tell you. If you look here, the Fahrenheit scale, where water freezes at 32 on the Fahrenheit scale, it's 0 on the Celsius scale. Very easy to remember. Where does water freeze on a Celsius scale? 0. Where does it boil? 100. You can see all these temperatures are equivalent on the different temperature scales. So water boils at 100 degrees. Very easy to remember. I know a lot of people have family in Europe and in Asia and there. And when you hear temperatures, you know, they'll tell you, oh, what's the temperature today? You'll ask them, oh, it said it's 23 degrees. They'll say it's beautiful. 23 degrees is obviously not a Fahrenheit scale. It's on the Celsius scale. 23 Celsius is around 68 to 70 degrees on the Fahrenheit scale. So there are different, I want to explain, those are two different temperature scales. And the United States is one of the only countries, and I don't know how many more there are, not very many, that still hold on to the Fahrenheit temperature scale where water freezes at 32. But in Celsius, that 32 Fahrenheit is equivalent to 0 Celsius. Also, I want you to note here, the coldest temperature that we can get to on the Fahrenheit scale is minus 459 degrees Fahrenheit. That is the coldest you can get. 459 degrees Fahrenheit is the same as 273 degrees minus 273 Celsius. That's the coldest anything can get. And what do I mean by the coldest? And this is important. It's because all thermal motion stops at those temperatures. That is, I told you, everything in the universe is made of atoms, and the charges in the atoms are always moving, creating electromagnetic energy. But when you get to that lowest temperature, which we call absolute zero, at absolute zero, here it is here, absolute zero, all thermal motion ceases. That is, there is not enough energy for the electrons to move, and they stay still. And if they stay still, they don't emit electromagnetic waves. So here's a case where electromagnetic waves do not come out of an object. And the reason they don't come out of the object is because it's so cold, it's at absolute zero, that the electrons and the protons just stop moving. Okay, you know, for example, if you're boiling water on the stove top, if you have it at room temperature, the surface of the water seems very calm. As you start increasing the temperature, you see the start of the water starting to bubble. It starts getting more violent. That's because heat energy is making the atoms move faster and faster. The more heat, the faster they move. The colder it gets, the slower they move, till finally at absolute zero, they'll get very cold and they cannot move anymore. But there is nothing that we know that's at absolute zero. Nothing in the universe we know is at absolute zero. They may be very close. They may be a millidegree or a thousandth of a degree above absolute zero, but we don't know of anything that's at absolute zero. And so those are the two temperature scales I talked to you about before. But scientists use a third temperature scale, which is probably one of the easier ones to remember, and that's called the Kelvin scale, which you can see on the right-hand side there. The Kelvin scale is a scientific scale where absolute zero is represented by 0 degrees. So when you say something is at 0 degrees Kelvin, it's at absolute zero. Where water freezes at 32 degrees on the Fahrenheit scale, it's at 273 degrees Kelvin. So 273 Kelvin is the freezing point of water. 373 Kelvin is the boiling point of water. So we have a reference. You can see that the freezing point of water and the boiling point of water are separated by 100 degrees Kelvin. So the Celsius and the Kelvin scales looks like they're off by a factor of 273. So if you have a temperature on the Celsius scale, just add 273 to it, and that's the temperature Kelvin. So what I want you to remember from this slide is the scientists use the Kelvin scale, and 0 degrees Kelvin represents absolute zero. And what's so special about absolute zero? What's special is all thermal or molecular motion ceases. Charges stop moving. They don't give off electromagnetic waves anymore. So if something is at absolute zero, it's not going to give off electromagnetic waves. Okay, hopefully we got that. So let's go further. In general, what I want to show you is this chart here gives us what it's called the black body spectrum. A black body in physics, okay, is a body that's an ideal radiator of electromagnetic waves. That is, it can emit electromagnetic waves and absorb electromagnetic waves. Okay, that's what a black body is. So a black body spectrum then is a measure of how much radiation comes out of a material based on its temperature. Temperature is now, you can start seeing, hopefully, is the key factor in the emission of electromagnetic energy. If the temperature is close to zero, there will be no electromagnetic energy released. However, as soon as the temperature creeps up a little and the charges inside the atoms begin to move, electromagnetic energy is released. And the warmer we get, the more and more electromagnetic energy is released, and released over a broader range of frequencies. And that's what this is designed to represent. This is how strong, on this one, how strong the electromagnetic waves are. That is how many of them there are, and this is their wavelength. We start with very long wavelength, and we go to very short wavelength. So we can see here, if an object is at some temperature, okay, it's going to have some of the long electromagnetic waves, and they start getting shorter and shorter and shorter till they reach a peak, and then all of a sudden it drops here. The shape of this curve, a slow rise followed by this little peak, that descending peak. That is what we call a black body spectrum. So for an object, each object at any temperature will have a bunch of radiation coming out of it that looks, when plotted, looks like this. There are all different wavelengths here. Notice that this encompasses quite a few wavelengths. And because an object is at a certain temperature, it will have more or less spread. Obviously, if it's colder, the spread of wavelengths is smaller. If it's warmer, the spread of wavelengths is going to be higher. And this peak right here, the peak, this is where most of the radiation is, will occur. For example, this is at a certain temperature. The peak occurs at whatever wavelength this is. And if it's colder, this curve moves to the left. And if it's warmer, this curve moves to the right, meaning to the left, longer wavelengths, to the right, shorter wavelengths. So temperature is what determines this black body spectrum. All right, and what I want to show you is, let's look at the black body spectrum for a few objects at a few different temperatures. Okay, here are 4 different black bodies, okay, or 4 different objects at 4 different temperatures. The first is an object at 60 degrees Kelvin. 60 degrees Kelvin is relatively cold. Remember, 273 Kelvin is the freezing point of water. So this is below freezing. So this is the spectrum. This is the radiation, okay, that would come out of an object at that cold temperature. Notice that here's the shape that I talked to you about, okay? And notice this is the longer wavelengths and these are the shorter wavelengths. And notice there's a little rainbow in the center here. That shows you where the visible spectrum is in the electromagnetic spectrum. You'll see where that is located. So you can see here the only radiation that comes out of an object at 60 degrees Kelvin is right here. It peaks at this place, at this temperature right here. It peaks at 60 degrees Kelvin. Okay, that's where at 60 degrees Kelvin, most of the energy comes out here. What wavelength is that? Well, 48,000 nanometers. Okay, a nanometer is a billionth of a meter. Okay, is 10 to the minus 9, a billionth of a meter. That's its wavelength. That's a relatively long wavelength, 48,000 nanometers. So what I want you to see is here's an object at 60 degrees Kelvin, and notice that the only amount of radiation that comes out is below the visible. So if we look in the sky, if we look at it, what do we see? Well, if you can ignore those little white lines there, it's black. You see nothing in the visible because none of this radiation is crossing the visible region of the spectrum. And if nothing crosses the visible region of the spectrum, we won't see it. That's why it looks black. Let's look at another object. Let's look at the next one down here. Here is an object that's hotter. It's at 600 degrees Kelvin, okay? That's pretty warm, okay? And its peak here, this is around at the 600 degree Kelvin point, that would be the peak right here. And the peak wavelength that occurs at, notice it's starting to get shorter. Now it goes to 4,800 nanometers. It was 48,000 at 60 degrees. And what I've done is I've gotten 10 times hotter. I've gone to 600. And now the wavelength is 1/10 the peak wavelength. Notice now also that some of the wavelengths leak into the visible part of the spectrum. Some of them are visible. If you look real close, it looks like it crosses the visible in the red, yellow, and maybe some of the green part of the spectrum. So here's the object. Look at that. What colors are in it? Red, yellow, and maybe a little green. Those are the colors that are in there. That's why you can see the object, because now it's emitting electromagnetic radiation at a wavelength that your eye is sensitive to, and you can see it. So, again, let's look at this other black body curve. Here's another object. okay, familiar to all of us. Okay, what's that? The sun. The sun is at a temperature of about 6,000 degrees Kelvin. Okay, and if we look at the black body curve of the sun, the black body curve of the sun, notice that what's happening is the width of this curve is increasing. I go from cold to a little warmer to even warmer still. More and more wavelengths are coming out. Notice that the electromagnetic spectrum of the sun peaks right in the middle of the visible spectrum. That's where its peak is. Okay? Right in the middle there in the yellow. So, what color do you think the sun is? Of course, it's yellow, right in the middle of the visible spectrum. And you can see that wavelength of the yellow light is listed right there under the 6,000 degrees Kelvin. It's 480 nanometers, 480 billionths of a meter. That's the length. That's a very, very small wavelength. That is the wavelength of yellow light. And most of the energy of the sun comes in the visible, and it peaks right in the center. And a very interesting thing to notice is that the peak of the sun's energy, boy, by coincidence, why is it right in the middle of the visible spectrum? That's where our eye is most sensitive to. Well, as humans developed on the surface of the Earth, based on radiation that's hitting the Earth from the sun, because the sun peaks in the middle of the visible spectrum, our eyes have become adapted to being more sensitive to yellow, because that's how we evolved. We evolved in the light of the yellow sun. So our eyes naturally would be tuned to the yellow part of the spectrum. So the reason, okay, we can, our vision, the yellow of the sun comes from the fact that, one, the temperature peaks there, and also our eyes are most sensitive to the color yellow and probably more yellow-green. Oh, they're sensitive to that because that's how we evolved. We evolved under the light of the sun. So our eyes adapted to be more sensitive to that wavelength. That's why we can see in the visible part of the spectrum. You can also see that some of the radiation, notice it falls down here. This is above the visible region of the spectrum. And if you remember, the next category was the ultraviolet. So the sun puts out a lot of ultraviolet waves too. And as you remember, some of those ultraviolet waves give you a suntan. Okay? Some of that ultraviolet comes through our atmosphere, but most of it is blocked. That's how we get a suntan. So you can see, based on temperature, this is the way how much radiation comes out because of temperature. And finally, we're going to the highest temperature of all. Let's go 10 times higher than we were before. Let's go to 60,000 degrees Kelvin. Really, really hot. And now you can see the curve has actually gotten a lot wider. Okay, because now we're at a lot of temperature. There are a lot of different wavelengths that come out of this now. Because of the motion of all the atoms being at a high temperature, that a lot of radiation comes out from the radio through the visible into the ultraviolet and probably into the X-rays also. So this object, notice as it crosses through the visible right here, as it crosses, the most sensitive area, the highest amount of radiation comes out on the blue side, on this side right here, rather than this. And that's why the object looks like a little bluish. Notice it looks a little blue, and that's because the peak in the visible is in the blue, so we see the most of the radiation coming out in the blue. However, the peak of the radiation of this object being very, very hot is not in the visible, but here, either in the high ultraviolet or even in the X-ray region of the spectrum. So the key thing to remember here is that temperature determines how many electromagnetic waves come out and at what wavelength. Okay. As you get hotter and hotter, the electromagnetic spectrum gets wider. Okay. And if it crosses the visible, if it goes through the visible, we're sensitive to those. We can see those things. But if there's no radiation in the visible, we're not going to see it. And we need other instruments to be able to see it. So hopefully that gives you a little better understanding of that concept of black body radiation and about temperature and its influence on electromagnetic radiation. Let's look at this now. We want to talk about spectroscopy. And you actually used a spectroscope in one of your lab courses. If you remember, I don't know how you did it, if you were there, did it live when we were still having classes, or you did it online. You were actually able to look through an instrument and have the light pass through the instrument, and then the light would actually pass through this instrument and break up into all its different colors. Here's an example here of what's called a spectroscope, because it helps us look at some of the electromagnetic spectrum, essentially only in the visible. This is a visible spectrograph. All right, and the way this works is a light source, and this light source here is we have a light bulb, and you know a light bulb, you pass electricity through it, and the filament heats up, right? That heats up and it glows, all right? It glows, and it glows at a temperature that you can see it because it's in the visible part of the spectrum. So the visible light coming from the heated light source goes through, let's say a lens, this is just to focus the light, and it goes through a little slit right here, and then it passes through a prism. And a prism is a piece of glass, and if you remember, that glass will actually bend wavelengths all different. It does refraction. And when white light, when a broad source of light, like from a light bulb, all different colors, that's really white light, when it goes through a prism, it'll break up into its colors. It breaks up into the red, yellow, green, blue. It breaks up into all those colors. The red bends the least. As you can see here, bends the least. The blue bends the most. And if you look on a screen of the output from the spectroscope, you will see all the different wavelengths. You can see all the colors. It looks like the colors of a rainbow. That's the continuous, what we call a continuous spectrum, because we have a continuum of colors. They're all from red, yellow, green, blue, violet. They're all there. Okay. The light source has white light coming out of it, and white light is made up of many different wavelengths. And what the spectroscope does is it breaks up the wavelengths into so you can see their individual components. And this type of spectroscope, this one right here, is a continuous spectrum. When you see a rainbow of colors coming out, these are all the different wavelengths that are contained in that light bulb right there. I want to talk to you about two other different kinds of spectroscopes and two other different kinds of spectrums where now we're going to change the light source. We're not going to put light from a bunch of different wavelengths in there. We're going to change that. Let's look at that next. So we're leaving this continuous spectroscope, and we're going to look at this one. This is called an emission spectroscope. And now you can see I've changed the light source. The light source now is a vessel that has hydrogen gas, a single element only of hydrogen. Hydrogen is heated up until it glows. Normally hydrogen you couldn't see hydrogen. Hydrogen is in the air around us. We can't see it, but if we heat it up enough, it can start glowing in the visible. We'll raise some of the wavelengths that go through the visible. So if we heat this hydrogen gas, and typically the way it's heated is, if you remember in the lab, I don't know of how much you did, but you pass an electric current through a hydrogen gas, and that electric current heats it up so the hydrogen gas glows. And it's got some color, right? It heats up so it's invisible. And when we pass that hydrogen gas, the heated hydrogen gas light through a prism, it's also going to, the prism will separate it according to wavelengths. It will refract the electromagnetic radiation, or the light coming from that heated hydrogen gas. And lo and behold, what we get when we heat a single element, not a broad range of elements, is a spectrum that's mostly black. If you look here, the spectrum is mostly black, and it has a series of lines on it. You'll see for hydrogen, I get a red line, a green line, and a few blue lines. This is called the emission spectrum of hydrogen. So if I had a glowing gas of hydrogen and I put the hydrogen light through a spectrum, I'm going to get an emission spectrum. I don't see that continuous colors. I only see very discrete colors. I see those specific red, green, and blue lines. That's called an emission spectrum. And an emission spectrum is very similar to a barcode. That is a barcode for hydrogen. Every hydrogen atom in the universe, that if it's hot enough to give off light, if we pass it through a spectroscope, we can detect its presence by looking at the emission spectrum for hydrogen, that barcode of hydrogen. Just the way barcodes are read in the supermarket to identify what that element, what product you've bought, the emission spectrum will tell us what element that is. So this is a different kind of a spectroscope. It's an emission spectroscope, and it's because we have only a single element, and we can identify that single element if we heat it up enough so that the radiation can go through a prism and go up on a screen. So an emission spectrum usually has a black background with just a series of lines on it. And those lines are a barcode essentially for that element. And here you can see these are emission spectrums of several different elements. This is the fingerprint or the barcode for this. So if we're looking at a star up in the sky, up in space, we can tell what elements are on it by passing the light through this type of a spectroscope and looking for the emission spectrum. You can see here in the top spectrum right there, that's the barcode for hydrogen. You have a red line, a blue, look like a teal colored line, and then a few darker purple lines. When you see that spacing of line, that characteristic spacing, that's the characteristic of hydrogen. Also, let's look at another element down below. The next one there is sodium. Look at sodium. Sodium has two yellow lines right next to one another. This is essentially the barcode for sodium. So if you were to pass some light from a star or something through a spectroscope and you see those two lines, you know you've identified sodium. The next one there is helium. Look at helium. It has a combination of the hydrogen lines and some yellow lines of the sodium. It's got a bunch of lines. That's the barcode for helium. And if you did the lab properly, if you remember, you look through the spectroscope and you had to match up the lines that you saw with a chart on the wall to try to identify the element. That's because each element had that barcode. Okay, you can look at neon, about the fourth one down there. Look at neon. Look at all the red lines of neon. And it goes up to the yellow, then it stops. That's the barcode for neon. And below that is the barcode for mercury. So anytime you want to detect an element, and I only have a few listed here, if we know what the emission spectrum is of that element, we can identify it. Okay, we can identify it in space. Okay, so those are the wavelengths down below. You can see the red wavelengths are the longer ones. You can see here, we're talking about wavelengths that are like 650 nanometers, remember billionths of a meter, to around 350 nanometers. This range from around 600 or around 700 nanometers to around 300 nanometers. That's the range of the visible spectrum. The visible spectrum goes from about 700 on the long side to around 300 on the short wavelength side. Those are the wavelengths that we're most sensitive to. And this is why this is a visible spectroscope, a visible emission spectroscope. And now, not to complicate things any further, but I want to show you one more type of a spectroscope. Let's look here. We're going to talk about now an absorption spectrum. And here's the basic spectroscope that you can see here again. It has the prism. Light is going through a prism, and light is being refracted, okay, because it slows up when it goes through the prism. It goes onto a screen. However, now we've complicated the light source. We have our bulb, the light bulb, which we know gave out a broad range of wavelengths. We know that it formed what we called a continuous spectrum. And now that light is going through another gas, but that gas is not hot enough to glow. So the light is just going to pass through the gas and then go through the prism. So here we have that continuous spectrum from the hot bulb, pass through the gas, and what do we have? Okay, what we get is this absorption spectrum. You'll notice that the spectrum contains a continuum. It has that broad range of wavelengths, the red through all the blues, they're all there. However, there are now some dark lines. There's like some material missing. Something is missing there. What's missing this is why this is called an absorption spectrum. And let me explain why we have absorption. What could have absorbed or removed some of those wavelengths? Here's what did it. This gas. This gas, as light passed through the gas, some of that wavelengths were absorbed and therefore are missing. That's why you see these black lines here. Let me show you the next chart here. It shows you a little better what the absorption spectrum looks like. Here's an absorption spectrum of hydrogen up on top. You can see if that cool gas that was in the way of the light bulb, if that gas is made of hydrogen, hydrogen is going to be absorbed. You noticed this was the emission spectrum of hydrogen here, remember, where the lines were glowing. If it was hydrogen only, it would show us a bright line. But now hydrogen got absorbed. It's the same exact line. It's just missing. And this one here is missing. These here, notice they're black. They're missing. That's why they're called absorption. And what I've done here is essentially I've identified the gas that light has passed through. It's passed through hydrogen because I can see hydrogen was absorbed. And this kind of a spectrum is called an absorption spectrum. If I have a continuous spectrum with dark lines on top of it, that's called the absorption spectrum. And the absorption and emission spectrum are just about the same. You can see they're exactly the same. The lines line up. However, they're bright in the emission spectrum, but they're dark in the absorption spectrum. So we can identify. And why is it important now to understand light passing through a gas? Well, because when we look at stars in the universe, the stars, their surfaces emit light, and their atmospheres, some of the light goes through the atmosphere and gets absorbed. So we can actually tell what the atmosphere was made of without even going there. We can just look at that light coming to us, and we can tell what material is surrounding the star. And we can also tell what temperature the star is at by what type of radiation and where it peaks. We can tell what its temperature is without even leaving the Earth. It's amazing that you can do it with this kind of spectroscope. Okay, so there's three types of spectra. There's the continuous, there's the emission, and there's absorption. I want to explain to you here another way we can see the absorption spectrum. We can see the absorption spectrum of the sun. Here's the sun, and the surface of the sun glows because it's at 6,000 degrees Kelvin. Okay, it's very hot. Remember, we showed that a few slides earlier. We showed the temperature of the sun. The sun is going to glow as a continuous spectrum. The surface of the sun puts out a continuous spectrum because the material in there is at all these different elements at different temperatures. We see the continuous spectrum. But then what we know in the outer layers of the sun, this light, this continuous light, has to pass through the gas, the outer atmosphere of the sun. And as a result, what do we get? We get an absorption spectrum. So the sun, this is the absorption spectrum of the sun. And we can tell here, the continuum tells us that it's a material that's emitting a broad range of wavelengths, and surrounding that broad range of wavelengths must be some gas that's absorbing these specific wavelengths. And if we match up that barcode to all the elements, we can identify what elements are in stars. Specifically here, this is the sun. So if you were asked what type of a spectrum the sun has an absorption spectrum. Okay, just like finally that last spectrograph that you saw creates an absorption spectrum. Okay, so just a summary. Some of the either solids, liquids, or gases, they produce the continuous spectrum. Okay, a cooler gas, okay, produces an emission spectrum, and then finally the absorption spectrum. Okay, here are the three different kinds of spectra. Okay, the hot gas, the light bulb you can see here, the cold gas, you can see the continuous, emission, and absorption, the three types of spectra. And if we look at those lines, if we actually plot how bright the colors are, or how bright the light is coming out, here's an absorption line you can see goes dark, and an emission line also shows up as a brighter part. So here's a dark absorption line, here's a bright emission line. So when I look across this absorption spectrum, if I look across it, I can actually determine what material is there. And that's how we've learned what stars are made out of, what temperatures they're at. We can tell the temperature by where the radiation peaks, where the peak of that black body curve is. We can tell what their temperatures are. And then we can also tell the materials that are made up of them. So you can see this is an important thing to understand is about this electromagnetic radiation and the fact that because the charges in the atoms are in motion, they release electromagnetic energy. And the temperature determines how much they move. And the more they move, the more electromagnetic radiation comes out. And we can analyze that radiation with this device called a spectroscope. And that's why that lab was devoted to doing that type of spectrum. And let's summarize here. Here are those three spectra. Here's the three spectroscopes. One, we have the continuous spectrum there on the bottom. Okay, where a light bulb, the light from a from a source containing a lot of different wavelengths passes through a prism and we get a continuous spectrum. However, if we have a single element, like hydrogen, we used the example before, and we heat it up till it glows, the light coming from it is not continuous, but it's very discrete. It's an emission spectrum. It's bright lines on a dark background. That's the emission spectrum. But then if we somehow, just like we represent stars, where light from the surface of the star has to pass through the atmosphere, through the cloud, it can get absorbed, and we get an absorption spectrum, which is a continuous background with dark lines across that, showing material has been absorbed or it has been removed. So these are the three types of spectra: continuous, emission, and absorption. Try to remember which ones are which. Continuous, as I told you, is a rainbow of all a rainbow of colors, continuous colors. An emission spectrum is just a black background and just the bright lines coming from that individual material. So if we were looking at, what an example, how do we see emission spectra? Stars give us, we said, absorption spectra. But emission spectra, if we have a cloud of gas, like a nebula in the universe, we can actually tell its temperature by looking at the glowing, at the way how it glows, the color it glows. It's going to give us an emission spectrum. So typically nebulae will give us emission spectrum because it's just gas at some temperature, a single element or multiple elements, and we can see all the elements that are in that nebula. But if it's a star that's at a lot higher temperature, it has that absorption spectrum where the continuous light coming from the surface has to go through the atmosphere, and the atmosphere absorbs out and actually tells us what material is in that. So spectroscopy is a very powerful tool in astronomy and helps us learn remotely what's in an object that's hundreds of thousands, if not millions of light years away. Without even traveling there, we can tell its temperature and we can tell what material makes it up. And that's a very important thing to be able to do. And that's why this lab, you did that lab on the spectroscope, so that hopefully now with this knowledge you understand a little more of what goes into that type of emission of light. Okay?